In this problem, I want to look at an application of the normal distribution. We are told in this example that the birth weight of newborn babies is normally distributed. Just given that information, I know if I were to look at a histogram, if I were to look at a relative or just a frequency or a relative frequency graph of the data values, we know if it's normally distributed, it's going to follow a bell curve. In this problem, the mean birth weight of all newborn babies is approximately 3,425 grams. So given that information, I can label my mean as 3,425, and I'm talking about grams. The standard deviation in this example, knowing that this is normally distributed, the standard deviation, or sigma, is 550. And we know that that value of 550 is giving us an idea of how far are the other values. How spread out is this data? Well, the 550 is giving us an idea. So the first thing we want to do, and I'm going to answer both of these questions. On this page, I'm going to answer the first part, where I'm going to draw a bell curve and label the mean and plus or minus 3 standard deviations. And on the next page, I'm going to answer this question, where I'm actually looking at an application of the mean and standard deviation to answer a question, so I can calculate a percentage and related to a particular observation. So first, I'm going to focus on this problem here, where I want to draw a bell curve and label the mean and plus or minus 3 standard deviations, given what I know about this population. So I'm going to draw a bell curve. I'm going to try very hard to draw a nice bell curve. That's not so bad. And what I know about a normal distribution is that the mean is going to be right in the middle. So if I were to label the mean, I would be at, in this case, right in the middle of this distribution is 3,425, and this is grams. What I want to be able to do is label where the standard deviations are. So I know if I add one standard deviation, if I add a value of one standard deviation, notice that if I'm right here at one standard deviation away, this is not as common as the mean, and that's just a fact that we know about normally distributed populations. If I go another standard deviation, I am further away. I'm even further away from the mean. Notice that that's also not as common as either of the previous two observations we talked about. And then finally, if I go one more standard deviation away, that's even less common. Now, I could also, given that these are adding standard deviations in the positive direction, I could also consider observations that are to the left of the mean. So what if I take away one standard deviation? Where am I going to be relative to the mean? If I consider observations that are even more to the left, if I think about what about 2 standard deviations away? And finally, 3 standard deviations. So what I would like to do is, given this information, I want to figure out what value, what birth weight is 1 standard deviation away in the positive direction and negative direction. What birth weight is positive 2 standard deviations or negative 2 standard deviations away. And then finally, positive 3 and negative 3. So let's focus on this positive side first. If I am 1 standard deviation away, then I know I'm going to be adding. I'm starting with the mean of 3,425. And I'm adding 1 standard deviation. Well, each standard deviation is 550. So if you were to add this, you would get 3,000. This would be 975. So this value right here, if you are 1 standard deviation away, if a birth weight is an observation of 1 standard deviation away, it would be 3,975 grams. If I add another standard deviation, add another 550, then I'm going to be right here at 2 standard deviations. So again, I'm starting at the mean, and I'm adding 2 standard deviations. So if you were to add 2 standard deviations, you would get, in this case, 4,525. And that would be right here. This is the value of 4,525. And this is grams. Finally, right here at positive 3 standard deviations, if we were to add just one more standard deviation and add 550 to that 4,525, you would get 5,750 So that is this value right here at positive 3 standard deviations, 5,075 grams. So all I'm doing here is getting a visual of where these observations are. And you're getting an idea of not where they are, but also how common are they. So notice a birth weight of 5,075 is really not common compared to a birth weight of 3,975. Now going in the other direction, what if you started or you were to the left of the mean by 1 standard deviation? So if we take 3,425 and I take away 1 standard deviation, or I consider the value to the left, then what we would get is 2,875. So that would be right here, the 2,875 grams. If you were to subtract another standard deviation, if you take another 550 away, if your 2 standard deviations to the left, 2325, 2,325 grams. And then finally, one more, if you were to subtract one more standard deviation, 1,775 grams. 1,775 grams. So the idea here is that we can label our bell curve. Our bell curve, where, given that we know it's normally distributed, the mean's going to be in the middle, and then depending on the size of our standard deviation, in this case 550 grams, we can label plus or minus 3 standard deviations. You will absolutely need to be able to do this on an exam. Let's look at the next page, where we actually want to take this question, as we'll read on the next page, and apply this normal distribution to find percentages. Our second question, we are asked or told that a soon-to-be new mother was told that large babies are common in her family. She is concerned that her baby is going to weigh more than 5,000 grams, which is 11 pounds, quite a large baby. What we want to be able to do is to use this knowledge here from this problem, the idea of the normal distribution, to either, we don't want to really scare her, but we want to know, is there any statistical evidence to support this fear? Should she be worried that her child will weigh more than 5,000 grams? So the first thing that I would strongly recommend doing is just to kind of refocus your idea on the graph. And that is, we are looking for, or we know that in this case, the 3,425 is the mean. That's the middle of our bell curve. And what we're looking for in this case is we're describing an observation of 5,000 grams. So if I were to label 5,000 on this bell curve, I know that's going to be to the right of the mean. So let's just put 5,000 right here. 5,000. Now if you were to kind of go backwards, you would know, just given our chart, right? The chart our picture that we drew in the last slide, we saw that the 2 standard deviations to 3 standard deviations covered a certain range. So if you were to look where 5,000 is relative to our last picture, you would notice that it's somewhere between 2 and 3 standard deviations. But again, here what we're looking for is, here's 5,000, and what we want to know is what percentage of babies weigh more than 5,000 grams. So I am looking for this area. I am looking for this area right here. So this is what I'm looking for. I don't know this area or this percentage. Now in order to calculate what this is, you could, if you have access to a statistical software package, you could do that. If you have a graphing calculator, you could do that. Or we could use a z-score chart. And a z-score, remember, is just figuring out how many standard deviations away is this. So our z-score, if we were to consider the formula, it's our observation minus the mean divided by the standard deviation, which in this case, our observation is 5,000, and this is grams. Our mean, given in this problem, is 3,425 grams, and our standard deviation is 550 grams. So we notice that our observation is 5,000. When we subtract the mean, what we're getting is the size in terms of our maximum distance here, or our absolute distance between our observation and our mean. So I'm looking right there in that example, how far is this in terms of absolute distance? And then when you divide that by the size of the standard deviation, what you're going to get is how many standard deviations away are you? So let's plug this in. 5,000 minus 3,425. In the numerator, what I get is 1,575. That's how far in absolute distance it is. And when I divide that by the size of the standard deviation, when you divide that by 550, you get about, and we're going to round this to the hundredths place, about 2.86. This is telling you that the observation of 5,000 is 2.86 standard deviations away. I'm not sure what's happening with my pen here, but standard deviations away from the mean. That's how far this observation is from the mean. Now, why is that important? Because on our z-score chart, if we look up a z-score of 2.86 on the chart, let's see what we get. So what I'm going to do is look up 2.86 on the chart. So hopefully you have that printed out. I'm looking up 2.86. So if I go down to the positive z-scores, here's 2.8. That's right here. And I want to go over to the column relative to the 6 in the hundredths place. The value I'm looking for is 0.9979. 0.9979. Now consider what this is giving us. 0.9979, which is also, in this case, 99.75%. What this is, keep in mind what that's giving us is the area to the left. So this is the percentage below, in this case, 5,000 grams. This is the percentage below 5,000 grams. The issue and the problem is I'm not looking for this. That's important, but that's not the answer to this question. I'm looking for the area above 5,000. So if 99.75 lies to the left, what I can do is take 100% and subtract 99.75%, and what I will get is that area to the right. And what you would get is 0.25%. That is the percentage above 5,000. That's the percent of babies weighing more than 11 pounds in this case. So to answer this question, in terms of what would we tell this soon-to-be mother, we would say that given the percent chance of having a child weighing 5,000 grams or more is so small, 0.25%, although it's possible, the chances of that occurring are very small. It is highly unlikely that the child will weigh that amount. Now we want to be careful here because this isn't saying it's not going to happen. It's just very unlikely in terms of what we know about all babies' weights. This particular observation, 5,000 or above, a very small percent of all babies weighs more than that amount. So just as a recap, what I did was I know, given the last problem, the mean and the standard deviation. I drew a picture labeling the mean in the middle, and I drew also the observation that I'm considering, in this case 5,000. The wording of the problem indicates that we were looking for not just 5,000, but we were looking for the area to the right, or the percentage to the right. So when you find the z-score, in this case we found 2.86, and you look up that z-score on the chart, this chart that I give you is going to give you the percentage to the left. That gave us the percentage to the left. The problem is we were looking for the percentage to the right. So that's why we had to subtract from 100. If you draw the picture and you label it correctly, then this isn't just a memorization of, oh, I have to subtract it, or do I subtract it? You know based on the picture that you drew, that it makes sense to subtract from 100 because we were looking for the area to the right, not to the left.